divisible 10. So if I just do 10 to the 4 divided by 10, I get 2.51 approximately watts per meters squared. If you did numerical solve, you got the same answer, right? So we can use the process that we learned on the previous page in order to solve, but we could also use numerical solve because we have that tool available to us. Okay. The half-life T in years of a radioactive isotope can be modeled by this function. Crazy, I'm not even gonna try to like process it besides the fact that I see natural log, which is log base E, cool. K is the decay rate, T is the half-life. So the decay rate of hydrogen 3 is 5.5% per year. Find its half-life. Okay, so what is going on here? T is half-life. It's in years. K is decay rate. It's in percent. So if the decay rate is 5.5%, okay, that is K. Find its half-life, and that means T equals question mark. Cool, so we're just plugging in 5.5 for K. Notice we could leave it in percent in our unit of measurement because it already divided out 100 to turn it into the decimal form of 5.5%. So the function already encapsulates what's going on there. Okay, so if you put this into your calculator and just press enter, it's 12.3. Our unit of measurement is years. I think this process is super important for models that feel complicated. This model feels complicated. I would encourage you to write out those variables and label them and have that ready to go because I think it helps kind of just clarify the process for you. The half-life of uranium is 68.9. Okay, interesting. That is T, the half-life. It's in years. I can match that unit of measurement. A sampling containing 250 grams of this is obtained. Interesting. That doesn't really go anywhere, but I have a sample. And stored as a side product of nuclear fuel cycle. Okay, find the decay rate per year. Okay, so if I need to find the decay rate, that means I need to solve for I. And if I wanted to solve, sorry, for K, I got mixed up with the thing above. So if I wanted to solve for K using the formula that I have, this is the thought process we go through, right? Okay, I use this formula, which involves K, and then I need to have the half-life, which it told me what the half-life was up there. And I remember that because I labeled it just really quickly to kind of clue us in. And that's a process of you making a connection with that stuff and kind of saving it for later, for you to either see it later or at least kind of force your brain to really truly recognize what that is as you're going through the problem. So we know that T is 68.9, so we can plug in 68.9 equals the natural log of 0.5 all over the natural log of 1 minus K over 100. Okay, you could absolutely use the processes that we talked about on the previous page in order to isolate for K. It's going to be so many different steps in order to isolate for K, and I think that's crazy. So I would either numerical solve, or if you don't have numerical solve, y equals, find that intersection. We get that K is approximately 3 sig figs, 1%. I have to write out 2 zeros there because we have to leave it in 3 sig figs. Okay, now it says find the amount of U-232 left in the sample after this many years. Okay, so let me just kind of break down what's going on here. Years as a unit of measurement means that is this is a tough problem. This is going to be a tough problem for you on the test as well. We know that 68.9 is one half-life. So we could make that connection right away and being like, okay, how do I solve this, right? I could plug, okay, the thought process that I had as I paused, I was like, ooh, that's tough, is I can plug in years into here, but years is specifically a half-life, and making a connection with what we know about the context. A half-life is how long it takes for an item to decay to half of its value, right? So we talk about this a lot when we're talking about nuclear decay, or carbon decay when we're trying to carbon date something, right? The half-life tells us how long it takes for that thing to decay to be half of the value that it was, which is useful for a variety of reasons. So plugging in 100 years would indicate that we're saying that it takes 100 years for it to become a half, but that's not true. Because the decay rate's already set, the half-life is already set for U-232. The decay rate is 1%, and the half-life is 68.9. And so then, hopefully, that thought process of being like, wait a minute, no, in the context, that doesn't make sense. Okay, so then what do I do with this? Hopefully in that point, you're like, well, that's just one half-life, which means if I start with 250, I have reached one half-life, which means it's really just half of the initial amount. That what it means to be a half-life is that that is how long it takes for that amount to decay to half of what it was. So you could just do that, but that might be tough to tell. The thing is that the actual process is complicated. We have to create a new equation or a new process, and understand what the relationship is here in order to create that equation, in order to solve for this problem. And this might be the difference between a 6 and a 7 on a test. And I think each of you is fully capable of getting to this point if we can think about everything we've learned up to this point in this unit. We have a decay rate of 1%. This means that every year it goes down by 1%. Okay, so if every year it goes down by 1%, this feels familiar with other things that we've talked about. Maybe we can think about this as a new exponential model where it becomes 99% each year of what it was. Or we can think about this in terms of a geometric sequence, right? When it's decreasing by 1% continuously, or it's not a good use of the word continuous, but periodically, if it's periodically decreasing by 1%, every certain period it's decreasing by 1%, that is a geometric sequence. So, okay, I know that the initial value is 250 grams, but I need to recognize that A sub 1 is not 1 year. That's the initial amount. So that's actually year 0. So always pause and say, what does my notation mean with geometric sequences, right? That's super important for you to not make mistakes. Okay, maybe I write out the entire formula for a geometric sequence for me to kind of understand what's going on here. That's A sub n equals A sub 1 times r to the n minus 1. Okay, I have A sub 1. I can also figure out what my R is. If it's decreasing by 1% every year, then that means that every year it's 100% minus 1%. It's 99% of what it was the previous year every year. Okay, so that means that my rate of change, my common ratio, it's been a while since we've talked about this, my common ratio is 0.99. Okay, so I have all of my pieces in order to create the exponential model. A sub n equals 250 times 0.99 to the n minus 1. So you could have done this in the problem above and said, okay, 68.9 years later, except we would have to realize that that would be not 68.9 up here, but instead 68.9 years after 1. So 69.9 up here. Let me show you. Right? If it was 3 years later, you would do 1 plus 3. So 68.9 years later would be 69.9. So if we do 250 times 0.99 to the 60, one more, 9.9 minus 1, as if that's how the formula works, we get 3 sig figs 125. So not exactly, because we've rounded 1%, right? So we've used a rounded value, so it doesn't give us exactly what it would be at that time, but you can see that that's giving us the same answer. So we've created a function that agrees with this. Okay, but we don't actually want to solve for 68.9 years later. We want to solve for 100 years later. And now that we've talked about this, we are not finding a sub 100, we're finding a sub 101, because 100 years after 1 would be 101. Okay, so then that's 250 times 0.99 to 101 minus 1. Go ahead and tell me what that is. When you plug that into your calculator, you get 91.5, 3 sig figs, grams, which is how much is left. So it's decayed some more. So as pausing and assess, okay, yeah, it's decayed. It hasn't been a full half-life again, so it won't be half of 125. So we haven't quite reached half of 125, but we're definitely less than 125. That all kind of makes sense in terms of what the answer should be. So yeah, cool. That makes sense. Great job today. That one was a really tough one. As long as you can figure out most of these guys on your own, that's good. And you might have a question. You will definitely have a question that's this tough on the test. And so just be prepared for the fact that there are going to be tough questions that you have to be able to spot. That's a geometric sequence, and it's not told to you explicitly. So just trying to pause and think about how all these things work. Great job today.